Okay, so today I'll be talking about. Okay, today I'll be basically talking about. I'll be revise. So, where are we headed right now? So right now I'm going to start optimization for PDEs, which is basically a subset of machine learning for PDs. So say you want to basically solve for the heat equation ut is equals to uxx plus some f of u. So there is some nonlinear heat equation. And you want to solve it via neural networks. So the first thing that usually most people do is discretize the partial differential equation into a finite dimensional model. And then pose an optimization problem such that it basically solves your heat equation. So right now we are going to do optimization for PDs. So for that, I have talked about Sobolev spaces in length. Let's just recap things once again. So basically my lectures will go in two. So from now on, my lectures will be of 30 minutes. So 15 minutes I'll be teaching some theory, and 15 minutes MATLAB plus Python programming. Okay. So I'll just recap Sobolev spaces for 15 minutes and slowly we'll go to the optimization theme. So right now what I'll be doing is I'll just speak about Sobolev spaces, which is basically optimization space, and then how to solve variational problems. This is basically minimizing the cost function. So let me begin with the syllabus. So we'll be basically learning something about Sobolev spaces, and after Sobolev spaces I'll teach something called elliptical PDEs. After elliptical PDEs, I think I'll talk about the variational problem. Just a second. Yeah, so firstly I'll be talking about distributions and weak derivatives, then Sobolev spaces, and then I'll be talking about elliptical PDEs, and from here to optimization of okay. So basically the weak derivatives and distribution theory leads us to view linear differential equations as some linear functions on the space of test functions. So let me just start by defining a weak derivative. So this is a definition. So definition of weak derivative. A function f belongs to L1. I hope you remember what is L1 log. Is said to be all. Is said to be weakly differentiable to x1 xi if there exists a function g I belongs to L1 log omega such that this particular inequality holds. Integral of omega f dou I of phi dx should be equals to minus integral of omega g I phi dx for all phi belongs to CC infinity functions. So if this is satisfied, then gi is weak derivative dou if denoted by this. So gi is the ith weak partial derivative of f and it is denoted by dou if. So in this is basically equally written as integral of omega f dou if phi is defined omega dou if into similarly we can basically extend this to just a second. Yeah, so similarly we'll also give the definition for any multi-index derivative. So let alpha be a multi-index, a function f in L1 log of omega has weak derivative dou alpha of f in L1 log of omega of order alpha if integral of omega dou alpha of f phi dx is minus 1 power. I have taught what is multi-index in detail in previous lectures, so just to complete. For all phi belongs to CC infinity of omega. So I'll be giving an example. So consider this particular function f of x is equals to x if x greater than or equals to 0 and 0 if x less than 0. So this is basically this particular function. And what I claim, then for any phi belongs to CC infinity functions, integral minus infinity to infinity f phi dash dx is basically integral of 0 to infinity x phi dash dx, which equals minus integral 0 to infinity phi dx. This is basically, I have just changed the order of integration, which is basically minus integral minus infinity to infinity, the step function from 0 to plus infinity times phi dx. So now what does this mean? So this means that chi 0 to infinity is the weak derivative of this particular function. Okay, now I'll just go with this particular function. Now I'll just go with this particular example. Chi of 0 to infinity of x is basically plus 1, 0, x greater than or equal to 0, x less than 0. Minus infinity to infinity, chi of 0 to infinity phi dash dx equals integral 0 to plus infinity times phi dash dx, which is equals to minus phi of 0. So if basically considering the test function phi of 0, it follows that okay, so basically if the weak derivative exists, then it will satisfy minus integral to infinity f dash of phi dx is equals to minus phi of 0 for all phi belongs to cc infinity of omega. So considering all the test functions with phi of 0, it follows that f dash must be 0 almost everywhere. But then this basically gives a contradiction for the test function with phi of 0 not equals to 0. So basically the step function does not have a weak derivative. Okay. Now I'll just state a theorem. If f is weakly differentiable and f dash of 0 is 0, that is weak derivative of f is 0, implies f is almost constant. Okay, now I'll just give out a definition. So a function, a function f, not continuous maybe, a function f to r, it's okay, a continuous function is said to be Lipschitz if for some we have for all x comma y so a locally Lipschitz function is almost differentiable everywhere. So I'll just state this without proof. So just another theorem. A function which is Lipschitz is differentiable everywhere. So I'll just end the theory part today with the definition. So a function f from a to b to r is absolutely continuous for every epsilon greater than 0 if there exists delta greater than 0 such that sigma I for any finite collection of intervals such that this is the definition of absolute continuity. Okay, with this today we will just end the theory part. I'll begin with the simulations. Okay, so basically we last time I took some complicated heat equation, but let us go step by step. So I'll be starting with the finite element method. Let us solve this particular heat equation. Ut is equals to uxx plus chi times of some x of f of t. F of t is some input function. U of x comma 0 x comma 0. Initial condition is 0. U of 0 comma t equals 0. U of 1 comma t equals 0, right? So you just write. So previously I just explained about the weak form. You just multiply it with some test function. So this is how we basically link our weak derivatives to the PDs. So right now to solve the finite element method, we are multiplying it with some function phi and just showing that uxx into phi. Right. So this is our weak form of our heat equation. I'm just interchanging the order of integration. Right. Now we choose phi of x equals, you have integrate 0 to 1, say. Start choosing these particular functions as your hat functions. Linear splines. Phi of x is r minus I minus 1 delta r by delta r. I plus 1 delta r minus r by delta r. these are our test functions. And we approximate our u, we project our u into span of Vi's. So u is equals to, that is delta x actually. So sigma di of t into Vi of x. So once you plug the test functions into our weak form, right? So this will basically turn out to be m times d dot is equals to minus kd plus, so this is some stability margin that we consider, mu times md plus inner product of chi comma Vi into s of t. Okay, so your m of I comma j is basically integral of phi into phi j dx. Right, let us just compute the value of m matrix. So your m of I comma I is equals to integral 0 to 1 x minus so what's your phi of x? Phi of x is basically x minus I minus 1 delta x by delta x by I plus 1 delta x minus x by delta x, right? So I guess we'll be just computing the we'll be computing the values of the matrices M, F and everything tomorrow, and I think we'll simulate the heat equation by 2 days. I think by Wednesday we'll simulate the 1D heat equation, and then I'll go to Cartesian, spherical and so on in Python programming. Okay, we'll stop the lecture by this thing.